Hello everyone, I'm Norman Wahlberger. This is our third lecture on the 13th of our famous math problems, the rotation problem and Hamilton's discovery of quaternions. In today's lecture, I basically want to introduce quaternions to you. A lovely algebraic structure that requires four-dimensional space and gives a lot of insight and computational techniques for understanding rotations in our three-dimensional space. So it's a question of a higher dimension coming in and helping us in our three-dimensional situation. Okay, so the first two lectures in this series have already talked about complex numbers, and then we talked about rotations in three-dimensional space. And I remind you that complex numbers, which we can think of as things of the form u plus iv, were intimately connected with rotations in the plane. And that is really this connection that motivated Hamilton to ask, well, what algebraic structure plays an analogous role for rotations in space? That's our problem. And in 1843, he discovered that the answer was to use the quaternionic structure of four-dimensional space. Now, rotations in three-dimensional space had already been studied by Euler, who knew quite a lot about them. And aspects of the quaternion structure were also suggested by a paper of B. Rodriguez. That was prior to Hamilton's discovery. So in today's lecture, we're going to introduce quaternions and sort of orient us towards how we're going to use them for three-dimensional rotations. In putting together this lecture, I've been motivated by a lot of requests of various people to explain the theory of quaternions. And so I've decided actually to add a fourth lecture, because there's actually quite a lot to say about this subject, and perhaps this is going to be a somewhat self-contained treatment or introduction to quaternions. It's also going to have some novel aspects to even people who are familiar with quaternions, because I have a very rational approach to things, and this actually helps us in ways to steer us in interesting and good directions. Quaternions have had an up and down history, and but today they are seeing a big revival with lots of applications. First of all, in aircraft and spacecraft attitude systems, robotics, video games, kinematics, physics, very important, signal processing, graphics, and other subjects too. So more and more people are starting to appreciate the power of quaternions to understand motions in three-dimensional space. We're going to start by introducing quaternions and the operations on them in analogy with complex numbers. So let me remind you that complex numbers, typically something of the form z equals u plus iv, where u and v are rational numbers. So for me, there are really no irrational numbers, and everything should be expressible and understandable in terms of rational numbers, and that's how I'm oriented. Very good approach to have. Now, in the previous lectures, I've used not u and v, but a and a plus ib, or maybe x plus iy. I'm going to use u plus iv just here to motivate the movement to quaternions. All right, so I remind you that originally we defined complex numbers not in terms of u plus iv, but rather simply as an ordered pair of numbers. And that then we introduced the addition as pointwise, and then all the complexity is in this definition of multiplication, how to multiply two ordered pairs of rational numbers. And here was the familiar definition. So together, this addition and this multiplication give us an algebra structure on the space of complex numbers. So now we're going to introduce quaternions in an analogous fashion. Okay? But instead of having ordered pairs of numbers, we're going to have ordered quadruples of numbers. So we're looking at, say, vector, whose components are t, x, y, and z, where all these numbers, t, x, y, and z, are all rational numbers for us. So that's what a quaternion is. It's just a vector with four components. And the crucial thing is how we're going to add and multiply them. Addition is easy, it's just component-wise, just as it is for complex numbers. So this thing here plus this thing here is t1 plus t2, x1 plus x2, y1 plus y2, z1 plus z2. All the complexity lies in this multiplication here. And let's have a look at it. So we have two vectors, t1, x1, y1, z1, and t2, x2, y2, z2, and here's how we multiply them. We're going to get another 4 vector. Here's the first component, the second component, the third component, and the fourth component. The first one is t1, t2 minus x1, x2 minus y1, y2 minus z1, z2. The next one is t1, x2 plus t2, x1 plus y1, z2 minus y2, z1. And then the next one is t1, y2 plus t2, y1 plus z1, x2 minus z2, x1. And the last component, t1, z2 plus t2, z1 plus x1, y2 minus x2, y1. So this is the way we multiply quaternions. Now, there's an obvious distinction between the first entry, the t, and these other 3 entries, which we're calling x, y, and z. And it's often helpful for us to separate those more clearly. And we do that by introducing this alternate terminology of thinking of the x, y, and z as being a single vector, an ordinary 3-dimensional vector v. So an alternate notation is to write this as tv, where v actually represents the vector x, y, and z. When we do that, we can rewrite the operations in simpler fashion, at least shorter fashion. So t1 v1 plus t2 v2 equals t1 plus t2 v1 plus v2. That's just component-wise addition. And then the multiplication becomes the product of t1 v1 and t2 v2 is t1 t2 minus v1 dot v2. We're taking the dot product of the vectors v1 and v2, which you see right here. And then the next 3 components are all brought together in this vector expression. So this is a vector. So it's t1 times the vector v2 plus t2 times the vector v1. And there's an additional term, which is basically these mixed things here. That's the cross product of v1 and v2. So in order to write it like this, we have to have a prior understanding of the dot product of vectors in 3-dimensional space and the cross product of vectors in 3-dimensional space. But if we have such a prior understanding, then this is a much more concise and memorable way of writing the operations. Historically, it's interesting to point out that Hamilton introduced his quaternion structure before the idea of a dot product and a cross product had been clearly enunciated. That only came later on. The American mathematician Gibbs basically introduced those 2 notions. And then there ensued a great battle between the proponents of quaternions and the advocates of the dot product cross product point of view. The dot product cross product point of view eventually won out, and that's why in linear algebra courses these days students learn about dot products and cross products and rarely about quaternions. Nevertheless, the quaternion business actually came first. Now there's one additional useful thing to point out, and that's that this formula for multiplication in this form is actually very close to the formula for multiplying complex numbers. So if you imagine just taking this formula and replacing u's with t's, all right, then you see that this and this is very parallel. t1, t2 minus v1 dot v2, it's almost the same as that, except we're talking about the dot product of the 2 vectors, not just the product of these numbers. And then the next entry is just like this one here, except with t's instead of u's. t1 v2 plus t2 v1. The real difference is the addition in the quaternion case of this additional term v1 cross v2, which we don't have up here. So it's a way of remembering it. It's really just like the complex number formulation with an additional v1 cross v2 term tacked on to that second component. Now that we have the operations, the natural question to ask is, what are the laws satisfied by these operations? And they're almost the same as the laws satisfied by the complex numbers. Addition of quaternions is commutative. We can change the order and things don't change. It's also associative. It doesn't matter in what order we pair things if we're adding three quaternions together. However, there's a big difference when it comes to the commutative law for multiplication. Okay? So in general, Q1 times Q2 does not equal Q2 times Q1. So this is non-commutative multiplication. That is a very big difference between the quaternion structure and the complex number structure. So when I write this down, I don't mean for all Q1 and Q2. I mean, generally speaking, there are some situations where we can have commutativity of two particular quaternions, but it's not the general case. However, crucially, the associativity of multiplication does still hold. And this is really the fundamental driver of the subject, the fact that we have associativity of multiplication. It's really the non-trivial aspect to these laws. We have distributive laws as we do in the complex number case, but now we probably should write two of them because things are not commutative. So we have two distributive laws, and I'm writing Q1, Q2 here short for Q1 times Q2. So this makes the quaternions, which are often denoted by an H, bold H like that, that makes it into a non-commutative algebra. There are also some special quaternions which get some special names. So the quadruple 1, 0, 0, 0, we usually call that just 1. And the reason we do that is because if you take this particular one and you multiply it by any q, either on the left or on the right, you just get q back. So this really does act as a multiplicative identity in the quaternion story. And similarly, the vector consisting of all zeros, we'll call that just 0. That is the additive identity. If you add it to any quaternion, you just get the quaternion. All right, so these are some of the laws of quaternion arithmetic. How do we prove these laws? Well, in some sense, it's a straightforward exercise. We just have to verify that these things are true by expanding things out with general quaternions on the left and the right-hand side in all cases. But especially for this one, that's going to be a lot of work. And we're going to use a different approach. So there's a powerful tool that we're going to employ, which is worth pointing out. It's a general strategy for any non-commutative arithmetical situation in mathematics almost. The idea is that whenever you have something non-commutative, chances are it's related to the algebra of matrices from linear algebra. So even undergraduates who have never heard of non-commutative algebras and so on, they will very likely have familiarity with multiplying and adding matrices. For example, 2x2 matrices. And they will know that that's in general non-commutative when it comes to multiplication. So the strategy here, which is sort of at the heart of what's called representation theory, is to connect any non-commutative arithmetical structure to linear algebra, in particular matrices. When we can do that, then we can extract information and understanding from our understanding of the way matrices behave. So we're going to employ that same technique here, and it's a very powerful principle, very effective in this particular situation. So we're going to connect quaternions with the simplest kind of matrices, the 2 by 2 matrices. But there's a slight twist in that the 2 by 2 matrices that we're going to deal with are going to have complex number entries. Not just rational numbers, but complex rational numbers. And here's exactly what we're going to do. We're going to take a quaternion, entries t, x, y, and z, and we're going to associate to that this particular 2 by 2 matrix. It's going to be called M sub q. That quaternion is called q. M sub q is by definition the 2 by 2 matrix whose entries are t plus xi, y plus zi, and then minus y plus zi, and t minus xi. So the t and the x here, the first two entries, give us this term here, t plus xi. And then the next two entries give us y plus zi over here. And then the way to remember it is that when we go from here to here, we're just taking the complex conjugate, which replaces this x with a minus x. And when we go from here to here, we're taking the complex conjugate times minus 1. So this is just minus the complex conjugate of that one. So I hope that's reasonably easy to remember. And given any 2 by 2 complex matrix of this form, it's straightforward to read off the associated quaternion because the entries are just t, x, y, and z. Just read along the top row, ignoring the i's. Alright, so why is this a useful thing to do? It's a useful thing to do for the following somewhat remarkable reason. That when we take two quaternions, say q1 and q2, and take the associated matrices, then the product of these two matrices using linear algebra multiplication of matrices is another 2 by 2 matrix, which is exactly the one associated with the product of the two quaternions q1 and q2. In other words, we're getting another matrix of exactly the same kind whose entries t3, x3, y3, z3, and so on are obtained in this way from the entries here. So T3 is T1, T2 minus X1, X2 minus Y1, Y2 minus Z1, Z2. And X3 is this, and Y3 is this, and Z3 is this. These are exactly the components of the product of the quaternion Q1 associated with this, and Q2 associated with this. All right, so that's a claim. So it means that if we actually multiply these things out, then these coefficients that appear here are going to be given by these formulas, which are exactly the same ones that appeared on the previous slide in my original definition of quaternionic multiplication. So I'm going to leave this to you as an exercise to check, but let's just do one example or two. So let's, for example, look at, say, Z3. Okay? How would we get this Z3, which is the imaginary part of this entry here in the top right-hand corner? All right, so I remind you that to get the top entry in the right-hand corner, which is really the 1, 2 entry of this matrix, we take the first row of this matrix and the second column of this matrix, and we multiply them. So we go this times this plus this times this. Okay? And so the Z3 is going to be the imaginary part of that, the stuff that involves an I. So let's ask, all right, if I multiply this times this, and then I add this times this, where am I going to pick up an I? All right, when I multiply this times this, where am I going to get an I? I'm going to get an I by T1 times Z2, and also X1 times Y2. All right, so I said T1 times Z2. You can see that down here. And I also said Y2 times X1. You can see that right there. Okay, now the next term is this times this. So if I take this times this, where am I going to pick up an I? Well, there will be a y1 times minus x2, which is right here, y1 times minus x2. And there will also be a z1 times t2, which is right here. And those are the only places we're going to pick up an I, so that's exactly why this z3 that appears here is exactly given by this expression. So we've sort of checked that one there. I'll leave it to you to check the other ones. So this is a very nice association between quaternions and matrices. It means that when we are doing quaternionic multiplication and addition, we can simplify things by converting them to matrices first and then doing matrix arithmetic, either matrix addition or matrix multiplication. So in other words, we're saying that if you have the matrix associated to Q1 and you add to it the matrix associated to Q2, then you're going to get the matrix associated to Q1 plus Q2. Basically because all these entries are appearing linearly here. And this establishes that the matrix MQ1 times the matrix MQ2 is really the matrix MQ1Q2, the matrix associated to the product of the two quaternions. And I'll just point out that our fundamental quaternions 1 and 0 have associated matrices, which are usually denoted I, the identity matrix, and 0, the 0 matrix. So this is a very powerful computational tool if you're working with quaternions, is to, instead of having to make computations with these 4 vectors and have to remember the formula, you can just work with these matrices, and that way you don't have to remember the formula because the matrix multiplication is just the familiar one from linear algebra. Okay. So this also shows that there's an intimate connection between quaternions and 2x2 complex matrices of a particular kind. And that's going to be quite important in our laying out of the theory. This connection has many interesting aspects. And so our first application of that basic correspondence is to actually verify the laws of quaternion arithmetic to show that they actually follow from the laws of matrix arithmetic via this correspondence. So I'll leave that to you as an exercise to just make sure that you understand why this correspondence allows you to transfer properties of, say, addition and multiplication from matrices to addition and multiplication of quaternions. So in particular, the associativity of quaternionic multiplication does not have to be checked now directly. We can verify it indirectly because it's a consequence of the associativity of matrix multiplication that we know from linear algebra. Okay, there's some additional special quaternions that I want to introduce, and I also want to talk about their associated matrices. We've already talked about the quaternion 1, which is 1, 0, 0, 0, and that's associated to the identity matrix 1, 0, 0, 1. I also want to look at these other 3 basis vectors, which just have a single 1 in an entry and zeros elsewhere, and we're going to call them L, J, and K. Now associated to each of these 3 basis quaternions is a 2x2 complex matrix. And I remind you the way to get the matrix is we just look at the first pair here and think of that as a complex number. That's the complex number I. And then this one here is 0. And then here, from here to here, we just do a complex conjugate. And from here to here, we do a minus complex conjugate. Similarly, this one here gives us a 0 here and a 1 here. There will be a minus 1 there. And 0, 0, 0, 1 gives us a 0 here and an I here. And the minus complex conjugate is an I down there. And now you can see why, I hope, that I haven't used the letter I to represent this quaternion. Why not? Well, because we're already using I as the usual complex number in the entries of this matrix. So it would be inconsistent or confusing if I used an I there and another I there to mean quite different things. Right, so it's a a bit of a departure from Hamilton's original notation, but there's much to recommend it. All right, so now in terms of these things, here are the laws of quaternionic multiplication that Hamilton wrote down with his knife on this bridge in Dublin in 1843 when he was walking with his wife. So almost the same, except that I'm using an L instead of an I, and I don't think he had this second row here. So we see that L squared equals J squared equals K squared equals minus 1, and minus 1 is just minus this one here. So it's the vector whose first entry is minus 1 and then 0, 0, 0. And then L times J equals K, J times K equals L, and K times L equals J. So they're cyclically symmetric, these three L, J, and K. And these can be verified at the matrix level just by doing a matrix multiplication with these complex matrices. When we switch the order of these, then we get a minus sign. So you can check that J times L is minus K, and K times J is minus L, and L times K is minus J. Now in terms of these basis elements then, we can express a standard quaternion, t, x, y, z, in terms of t times 1, which we'll just write t, plus x times L, plus y times J, plus z times K. And then we can think about this, this triple here as really representing a vector in three-dimensional space, which will typically denote V. So we can think of this quaternion as being the t, the scalar part, and the v, the vector part, is a vector with coordinates x, y, z with respect to the standard basis ljk and not ijk as usually appears in engineering texts. So it's a small variant from Hamilton using L, not I. Now let's talk about the conjugation operation on quaternions, which is analogous to the conjugation of complex numbers. If q equals t, x, y, z, then the conjugate of q, denoted q bar, is by definition t minus x minus y minus z. So all three of the vector components are negated. And now there's a few exercises for you to do. The first one is to show that the matrix associated to the conjugate of q is the Hermitian conjugate of the matrix associated to q. It's usually denoted by a star. And what that means is it's the transpose of the matrix M sub q, all whose entries are complex conjugated. There's a standard operation in linear algebra with complex vectors and matrices. The Hermitian transpose or conjugate. And the second exercise, use the fact that this conjugation satisfies mn star equals n star m star to show that if you have the product of two quaternions, q1, q2, and you conjugate the product, then you're getting the product of the conjugates, but in the reverse order. So you're getting q2 bar times q1 bar. Remember that multiplication is not commutative, so the order does matter when it comes to multiplication. And when we conjugate the product, we get the product of the conjugates, but in the reverse order. And now we can talk about the quadrants of a quaternion, which again is analogous to quadrants of a complex number. If q equals t, x, y, z is a quaternion, we define the quadrants of q, and that'll be capital Q of q, to be q times q bar, which happens to be the same as q bar times q. And you can check that that's t squared plus x squared plus y squared plus z squared. Now we're using a little bit of a notational device here. So this is actually a number here that you see. These are numbers. Some of the squares of these numbers, that's another number. While this is actually, strictly speaking, a quaternion. All right, so what do we mean there? Well, we mean that it's the quaternion whose first entry is this number and whose other three entries are all 0. So for example, the quaternion 5 0, 0, 0, we're going to identify that with a number 5, just as we identified 1, 0, 0, 0 with a number 1. All right, so let's prove that this thing here actually equals this. So we're going to write this q as tv in vector form. So v is a vector, the vector x, y, z. And here's q, and then here's its conjugate. And how do we multiply these things? Well, I remind you that in the vector form, the rule is t times t, so t squared, minus the dot product of these two. So the two minuses give us a plus, and we get plus v1 dot v2. And then the vector part will be t times minus v plus t times v plus the cross product of this v and that minus v. But we all know, I hope, that v cross minus v, these are two vectors that are in the same direction, so their cross product is 0. And this t minus v and this tv all cancels, so we're going to get 0 here as the vector part. And we're just going to get then the number t squared plus v dot v, which is this thing here. There's the t squared, and there's the v dot v, the quadrants of that vector. All right, so this quadrants is a very important property of quaternions, and here's an interesting exercise to show that the quadrants of Q can also be written in terms of the matrix M sub Q. It's the determinant of that matrix. And so here now is probably the main theorem about quaternions that states that the quadrants of a product of two quaternions is the product of the quadrants of the individual quaternions. This is exactly analogous to our main theorem for complex numbers. And because it's such an important theorem, I'm going to give you 3 proofs. All right, so the first proof is directly from the definition. The quadrants of Q1, Q2 is by definition Q1, Q2 times the conjugate of Q1, Q2. But the conjugate of Q1, Q2 we saw was Q2 bar times Q1 bar. And now by associativity of quaternion multiplication, we can regroup the brackets, bracketing the Q2 and the Q2 bar inside together. When we do that, that Q2 times Q2 bar gives us the quadrants of Q2, which is a number. And because it's a number, it commutes with everything else, so we can bring it, say, to the back. Then the Q1 and the Q1 bar are together, like that. So then the Q1 and the Q1 bar are together, and we get that times the quadrants of Q2. And Q1 times Q1 bar is the quadrants of Q1. So we get the quadrants of Q1 times the quadrants of Q2. Here's our second proof. From the previous exercise, we saw that the quadrants of Q1, Q2 is the determinant of the matrix associated to Q1, Q2. All right, but the matrix associated to Q1, Q2 is the product of the matrices associated to Q1 and Q2. And the determinant of a product is the product of the determinants from linear algebra. That's the basic fact about determinants. And that then is the quadrants of Q1, and that's the quadrants of Q2. And now our third proof uses an identity. Just as our proof for the complex number situation rested on an identity of Fibonacci. Here the identity is more complicated, and remarkably goes back to Euler. So many things go back to Euler. So Euler discovered this remarkable extension of Fibonacci's, or Diophantus's, identity, which says that if you take t1 squared plus x1 squared plus y1 squared plus z1 squared, so that's a sum of 4 squares, and you multiply it by some other sum of 4 squares, then that product could be also written as a sum of 4 squares. And in fact, the entries in these 4 squares are exactly the coefficients of the product of the associated quaternions. t1, t2 minus x1, x2 minus y1, y2 minus z1, z2 squared, and then here are the other three entries. And this is an identity. It means that if you expand both sides, collect terms, you will see they're equal. This is called Euler's four-square identity, and he wrote it in a 1748 letter to his pal Goldbach. Now, at the time, Euler was not talking about quaternions. He was thinking about a number theoretical problem here, which is also another famous problem that we'll eventually talk about. The problem of whether an arbitrary natural number can be written as a sum of four squares. And so Euler struggled with that problem, but he realized that this was an important identity that sheds a lot of light on that number theoretical problem. And lo and behold, it's exactly what we need here to establish a third proof of this fact, because this is the quadrants of Q1, this is the quadrants of Q2, and this sum of squares is exactly the quadrants of the product Q1 times Q2. So Euler indirectly had this main theorem about quadrants of quaternions in this identity. Remarkable stuff. This quadrants allows us to write down a formula for the inverse of a quaternion. And it's exactly analogous to the inverse of a complex number. So the fact that Q times Q bar equals Q bar times Q equals the quadrants of Q, and this is a number, implies that if we want to find the inverse of Q, we just need to take Q bar divided by the quadrants of Q. In other words, if you take this and divide both sides by quadrants of Q, you get Q times Q bar over quadrants of Q equals 1. Right, so that's a formula for the inverse in terms of the quaternionic conjugate and the quadrants. And of course, in order for it to make sense, this denominator had better be non-zero. Now, fortunately, over the rational numbers, if we have a quaternion like this, then the quadrants is the sum of squares. That's going to be 0 only when the quaternion itself is 0. So over the rational numbers, this condition is really just saying that the quaternion is non-zero. I point this out in this fashion because, in fact, you can play this game of quaternions over other fields as well. It doesn't have to be the rational numbers. You can do this over a finite field if you're so inclined. It's not without interest. In that case, this condition is a little bit more complicated. It's possible for the sum of squares to be 0 and the entries not to be all 0. So in which case this condition really has some serious content. I just point that out as an aside. Okay, once we have the notion of quadrants, we could also talk about unit quaternions, which play an important role. Those are the quaternions whose quadrant is 1. Exactly analogous to the unit complex numbers, which of course play an important role in complex numbers. Alright, so in this case, the inverse of such a quaternion will just be the conjugate itself. The unit quaternions form the unit sphere. So the equation is t squared plus x squared plus y squared plus z squared equals 1. And that's an equation in four-dimensional space which describes or defines the three-dimensional sphere, which is usually called S3. So we're talking about a three-dimensional sphere in this four-dimensional space. And an immediate consequence of what we've been discussing is that this sphere is actually closed under multiplication and inverses. So if you have two quaternions who both have quadrants 1, then their product is also going to be of quadrants 1. And if Q has quadrants 1, then its conjugate also has quadrants 1. So this is in algebra called a group structure. So just as the circle or the unit circle in complex numbers has a group structure, so does the three-dimensional sphere in this four-dimensional space have a group structure. It's an important consequence of this quaternionic structure. And it's quite in opposition to the two-dimensional sphere in three-dimensional space, usual sphere, which does not have a group structure. There's no way of putting on a reasonable group structure on the two-dimensional sphere. One-dimensional sphere, yes. Three-dimensional sphere, yes. Two-dimensional sphere, no. That's an important ingredient in quaternions, this unit sphere. Now there's one more important sort of geometrical ingredient before we get to a picture that it pins down the geometry of this four-dimensional space, and that's the inner product. So there's a quaternionic inner product that's around, which is just analogous to the usual inner product in three-dimensional space. And here's the definition. If we have two quaternions, T1, X1, Y1, Z1, and T2, X2, Y2, Z2, we can define the dot product or inner product between those two to be this number, T1, T2 plus X1, X2 plus Y1, Z2 plus Z1, Z2. Exactly analogous to the way we define the dot product between two vectors in three-dimensional space. And then we see immediately that the quadrants of a single quaternion Q can be rewritten in terms of the dot product as simply Q dot Q. Alright, so your next exercise is to show that this inner product also has a natural expression in the matrix language. And Q1, Q2 is one half of the trace of the product of the associated matrices, but with a Hermitian conjugate on the second one. So it's one half trace of the product of MQ1 times MQ2 star. This kind of thing in linear algebra is quite a common thing, to find an inner product on matrices by taking the trace of a product, or the trace of a sort of Hermitian product in the complex situation. We're going to use that to establish this theorem here, that if you have three quaternions, say Q, Q1, and Q2, then if you take Q1 and Q2 and you multiply them both, say, on the right by Q, and take the dot product, then you're going to get something that's related to just the dot product of Q1 and Q2. The factor is Q, the quadrants of Q. All right? So there's a relationship between what happens when we multiply two quaternions by the same quaternion Q, say, on the right. What we get is that the dot product between them is multiplied by the factor of the quadrants of the quaternion we're multiplying by. And in fact, that's the same thing that happens when we multiply Q1 and Q2 by Q on the left. Alright, so here's a proof, at least the proof of the first part here. If we take Q1Q dot Q2Q, and if we believe this exercise, then we can write it as one half trace of MQ1Q, MQ2Q star. Now this MQ2Q star is the matrix of the complex conjugate of Q2 times Q. And then we can write this one here as MQ1 times MQ, and we can write this one as MQ bar times MQ2 bar. And then we can group those two together. And then the MQQ bar is going to be, well, this QQ bar is just the quadrants of Q. So this matrix becomes an identity matrix times quadrants of Q, and it comes out front. And what we're left with is Q1 dot Q2. And I'm going to leave the second part as another exercise for you to do, give you some practice in thinking about matrices and the connection with quaternions and linear algebra. All right, so this is a very important result, telling us that basically quaternionic multiplication is acting like a rotation, but scaled. So inner products are preserved up to a scaling factor. So it's exactly the same story that happens with complex numbers. When we multiply by a complex number z, what happens is the whole space is rotated and scaled. And that's essentially what's happening here with the quaternionic multiplication as well. While so far we've been talking about quaternions purely algebraically. and relating it to linear algebra. Now we want to have at least some kind of physical, geometrical understanding of what's going on. So we're going to try to draw a picture of this four-dimensional situation on this two-dimensional surface. And of course that means we're going to have to collapse things a little bit. We're not going to be able to view the whole thing as it really is. But nevertheless, I hope this will give you some orientation on how to think about things. So we're going to picture this four-dimensional space in the following way. Along this line here, that's going to be our t-axis. And perpendicular to it is going to be a three-dimensional space of the directions x, y, and z. So you should think of that as being like a plane, but it's actually a three-dimensional plane, which is actually perpendicular to this axis here. We might call that perpendicular three space capital V. That's like our familiar x, y, z space. And I've sort of drawn it here as a slab, suggesting something three-dimensional rather than two-dimensional. The actual x, y, and z axes I've also drawn. So here I say put the x-axis up and down, and the y-axis here, and the z-axis here. And you should think of these three axes as being a right-handed coordinate system in the usual way. Except that all of them are contained within this three-dimensional perpendicular slab to our scalar direction. I've also shown you the unit quaternion sphere, the S3, consisting of all the quaternions whose quadrants is 1. That includes the point 1. It also includes our basis vectors, L, J, and K, which lie on the axes, the x-axis, the y-axis, and the z-axis. Now this unit 3 sphere, of course it has an equator. So it meets this transversal 3 space V in a two-dimensional sphere. So one up from just having an equator. So there's an equator, but the equator is not a circle, it's actually a two-dimensional sphere. And I've tried to represent that by this green thing here. So there's a sort of part of that sphere, and then here's another part of it. So another direction. Okay. So that whole sphere, which is like S2, we can think of those as being the unit vectors inside this three-dimensional space V. Alright, so an arbitrary quaternion, say Q, out here somewhere, has a T component, and it has a V component. So if we project perpendicularly onto the scalar direction, we get some number, that's T. And if we project perpendicularly onto this three-dimensional plane here, we get some vector V. And so Q, which we can write as TV, or T plus V, there's the scalar and the vector part corresponding to these projected points T and the vector V up here. Okay, now I should also maybe say here's the conjugate of Q. It's T minus V. So it's what we get when we reflect this Q through this point T and an equal amount out the other side. That's the conjugate of Q. Okay, now we've now established some initial understanding of this algebra of quaternions and the units quaternions inside it. How are we going to relate this to rotations? How does this help us understanding rotations? Well, it all comes down to this formula right here. All right? So this is the formula that tells us how quaternions help us understanding rotations of three-dimensional space. Where is our three-dimensional space? It's exactly this space V that I'm talking about here. The space V whose axes are the x, y, and z axes in the usual way. It's the perpendicular hyperplane to the axis containing the 1, the scalar axis. That's going to be our vector space V, that we're going to be our three-dimensional space. And how does a general quaternion Q give us a rotation? So here's the formula. That phi sub q of r is a general quaternion anywhere, is by definition q bar times r times q, all divided by the quadrants of q. All right, so that's a linear transformation of r. There's an input r, the input's appearing linearly there. We're multiplying by q on the right and by q bar on the left. We have to remember the multiplication is not commutative. If it was commutative, we could change the r and the q bar, and then that q bar and the q multiplied together would cancel out with the quadrants of q on the bottom. We just get r. All right, so suppose that q happens to be this particular vector t plus v. What can we say about this transformation? Well, first of all, let's consider what it does to this point 1. Okay, so the point 1, if r is equal to 1, then this 1 here just disappears. So we just get q times q bar over the quadrants of q. They cancel and we just get 1. So necessarily that's telling us that this point 1 is always fixed by this phi sub q. The other thing that we know is that perpendicularity is preserved. This space V is consisting of the things which are perpendicular to 1, in the sense that the dot product between 1 and any vector V in here is 0. And by our previous formula, when we multiply by q on the right or q bar on the left, the dot products being 0 is going to be preserved. That's telling us that if r is actually in this V space, then the result of this will also be in the V space. Because it started out being perpendicular to 1, 1 is not changed, and so the output has to also be perpendicular to 1. So if we start with any vector r inside the vector V space, it's going to be sent to another vector in this V space. And it's going to be a rotation or possibly a scalar, multiple of a rotation inside this vector V space. Now the other crucial question to ask is, what's it actually going to do to the vector V itself, the V that's appearing here in this vector space capital V? So if our quaternion Q is t plus V, the question is, what happens to the vector V under this transformation? The interesting thing is that this vector V and this quaternion Q commute. Okay? Because V commutes with the t and V commutes with this V here. So this Q and this V commute, meaning that we can change the V and the Q there if r is equal to V. That's telling us then that previous analysis applies. The Q bar times Q will be together then, and then we'll cancel with this quadrants of Q in the bottom, and we'll just get V as an output. So we can see directly that this transformation is going to fix this vector V. And that means that it's going to fix the whole vector space, this three-dimensional vector space capital V, and it's going to fix the particular vector V. It's going to be a rotation of some kind about the axis through V. So that's how we get a rotation from a quaternion acting on this three-dimensional space. This is the picture that you should have when you want to understand how quaternions generate rotations of three-dimensional space. And it's this all-important formula that generates the rotations. All right, so I've gone through a lot of material in today's lecture. Okay, we've covered a lot of ground. So there's been a lot for you to do and absorb, and perhaps a somewhat unfamiliar aspect for many of you. But nevertheless, it's very rich and beautiful structure, and I'm going to talk more about it in our next lecture on this subject. I want to become a little bit more concrete and show you how this actually works in practice. So we have this theoretical framework now. How does it actually roll out if you actually have some concrete rotations that you want to make with graphics, or maybe you're making a video game, or maybe you're making some computation with rockets. How are you going to actually apply this kind of formula, and what's the connection between this quaternion and its coefficients and the amount of rotation that you're getting? This is a very interesting exercise. You can even think about it at this stage. So just how much are we rotating by? This quaternion t, we've said that it's going to give a rotation around the vector v. The question is, how much rotation are we getting? It obviously depends on t as well as on v. All right, so I hope you'll join me for that, our fourth lecture on this particular famous mathematical problem, a very important problem that has a lot of consequences throughout mathematics, but also with many, many applications. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.